Good evening, everyone. Welcome to the Simon Center and to this edition of the Della Pietra Lecture Series. We're very pleased to have as our lecturer today Professor David Gross from the Kavli Institute of Theoretical Physics at the University of California, Santa Barbara. David was the director of the Kavli Institute for 15 years and is the Frederick Gluck Professor of Theoretical Physics.
No.
No? He is?
I was.
No longer?
I have a different chair.
Was?
Should update your information.
The Frederick Gluck Professor of Theoretical Physics, and now he just wanders the streets.
No again.
The world. David is one of the leading physicists in the world today.
Yes.
And you don't need to take my word for it. He is renowned for his work on asymptotic freedom, which is a central part of what later became the standard model of physics, which explains the physics, all the physics we've been able to measure and see so far. For this work, together with his student Frank Wilczek and David Politzer, he won the Nobel Prize in Physics in 2004. After that work, he went on to be one of the founders of string theory, being part of the Princeton String Quartet, as it's known. So David is going to speak to us today about the frontiers of physics. Please welcome David Gross.
Sorry about that. Thank you, John. It really is a pleasure to be back here in Stony Brook, especially at this marvelous house that Jim built. And it's great to see this institute flourishing. So I've been for many years at a similar institute in theoretical physics, and I think such places are really important and marvelous, and it's great to see this one get off the ground and start, really functioning well. It's great. So I was going to talk today about the frontiers of fundamental physics, and which can be a dangerous term to use, especially in the presence of physicists from other fields of physics, which are, of course, equally fundamental. So let me explain what I mean by fundamental. I really mean elementary particle physics. The discovery and understanding of the basic building blocks of matter and the forces that act on them. And so, as Sean said, particle physics is in a very interesting stage now. We actually have a very comprehensive theory, which I will briefly describe my angle on it. We call it the standard model, but it's really a standard theory, amazingly successful. But the really interesting issues are those issues that suggest fundamental changes in our fundamental theory that go beyond the standard model. And I'll try to go rapidly through some aspects of the standard model before we get to the future and the unanswered questions. Now, physics is an experimental science. And the frontier of experimental high-energy physics currently is unfortunately not located in the United States, but in Europe, where our European colleagues have built and are running an amazing particle accelerator, which smashes protons together in a 20-kilometer ring that runs between France and In Switzerland, I'm sure you've heard about it. It's called the Large Hadron. Hadron is really a name for protons that are being collided together at very high energies. And when that happens, events like this occur, where two protons collide somewhere here. Often 20 or to 50 such events simultaneously or within a nanosecond, with incredibly large detectors. The pictures like this are taken. This, of course, is highly massaged. The software, hardware decides immediately whether to throw this event away, because in about a year they produce roughly 1 trillion such events. Million such events, and I can't imagine keeping the data for each event. So most are thrown away, but wisely within nanoseconds. So this is the incredible feat that our experimental colleagues are currently carried out, and that's the experimental frontier of elementary particle physics. These are a picture of one of the detectors, which I gather Stony Brook is connected to, Atlas, at the LHC. It's incredible construction of this I regard as the most complicated and interesting human effort since the pyramids, and more interesting than the pyramids, which were just tombs of pharaoh, dead people. But these things we actually learn about the structure of matter. And over the last century, and it's really not been more than a century when Rutherford first described the nucleus of atoms, and we began to unravel with the aid of quantum mechanics and observation and theory the structure of the atom. It's remarkable how rapidly we have come to a theory of the basic constituents of matter, the quarks that make up the neutron and the proton, the nuclei that make up the center of atoms, and the electrons that surround the nucleus in a cloud that's about 100,000 times bigger. And with the aid of quantum mechanics, quantum physicists have developed a sort of first version of the Standard Model, which is a theory of atoms and molecules, which accounts for most of the macroscopic world we see around us, including biology in a reductionist sense. But during the last century, since the discovery of the nucleus, frontiers of particle physics moved inward to discuss and study the properties of the nucleus. What are actually protons and neutrons made of? Quarks came along at some point. And most importantly was our understanding of the forces that act within the nucleus. One of the forces that acts within the atom, of course, is electricity and magnetism. That accounts for atomic and molecular structure. But within the nucleus, there are very short-range forces that were very hard to understand. And the culmination of our understanding of those forces and the discovery of these elementary constituents of matter are the ingredients that led to what's called the Standard Model. Now, the Standard Model is really a theory, full-fledged, successful theory. You can tell it's a theory because you can put the equations or the principle on one T-shirt. And given this T-shirt, in principle, with enough computing power and desire in a reductionist frenzy, we could, we believe, explain just about, not everything, fortunately, still work to be done, but just about everything that we have so far observed in the physical world. All sorts of parts of this Lagrangian, from which we know how to derive the equations of quantum field theory that that describe the electromagnetic, the strong, and the weak nuclear forces. And if we add a R to this, we can also describe, as Einstein taught us, the force of gravity. This has been an unbelievably successful model, which really should be called a theory. It's the most comprehensive theory that we've ever had in physics. There are a few parameters. For most cases of the physics around us, we only need a very small number of parameters. But for some rare events produced in such big accelerators, we might need all of the 19 or maybe a little more parameters. But given that, this is it, and it's all on one t-shirt. It consists of a list of particles, of basic constituents of matter. The origin of these particles we don't truly understand, I must admit, but they are observed, not just one so-called family of quarks that make up nucleons and leptons like the electron and its friend the neutrino, but as it turned out, 3 families for no good reason and no real understanding of their masses and mixings, the parameters that characterize the mass spectrum of the elementary particles, we don't understand. So we have to input the existence and the masses of these particles. What we do truly understand, however, are the forces that act on these elementary particles. And within the atom and nucleus, where we can ignore gravity, we have the force of electromagnetism. That's a familiar force to most everyone. Electric and magnetic forces that act on charged particles, and some of these particles here, up and down quarks and the electron, are charged, electrically charged. And then 2 other forces that act within the nucleus, which turn out to be also sourced by charges, and indeed, at a conceptual level, almost the same, conceptually the same as electricity and magnetism. Incredible surprise, at the end we ended up with just exactly the same forces that Faraday and Maxwell discovered and wrote down in the 19th century describing electricity and magnetism, except for the two small complications, or 3 perhaps. One is that in the case of the weak force, there are 2 charges. In the case of the strong nuclear force, there are 3 charges. And these forces are described quantum mechanically. They live in a quantum mechanical world. And there's an added ingredient that we had to add, or my friends had to add, called the Higgs field, the Higgs mechanism, one of whose precise predictions was, as you all know and have heard about, I'm sure, discovered last year, 2 years ago, almost 2.5 years ago, at CERN, at the LHC, the Higgs particle. This theory is amazingly successful. We've never had anything like it in physics. It works, as far as we can tell. It might fail at any moment, but there's no conceptual reason why it couldn't work down to the length that characterizes, we believe, since Max Planck discovered his constant, the smallest length where surely it will have to be altered severely, but that's 10 to the minus 33 centimeters, almost 16 orders of magnitude from where we now perform experiments. And as far as we know, and have tested, the same laws, interactions of these particles in atomic, molecular, nuclear, hadronic physics work all across the universe to the edge of the universe since its earliest history. 60 orders of magnitude. Now, when I was a student where we knew nothing about these forces and these particles, except for a few of them, like the electron, the idea that we would have now a theory which works over 60 orders of magnitude. Most people wouldn't trust a theorist to extrapolate by 1 order of magnitude, is truly mind-boggling. Now, I wanted to explain one of the main points I emphasized, that all of these forces are at conceptual level, at the bottom, the same. So electromagnetism, which is the force that most of us learn about even in elementary school, is the force that arises when you have electrical charges. And so, for example, this might be the electron, which has a negative charge, and its antiparticle, which is a particle with the same mass properties but the opposite charge, the positron. And as Coulomb, Faraday, Maxwell understood, they're the source of a field that permeates all of space, and the electromagnetic field, and gives rise to the force between these charged particles, which, as you know, is an inverse square law. It falls off like the square of the distance between these charged particles. This field has a physical meaning in its own right, and if you shake this charge, creates ripples in the field, which we indeed observe as light or radio waves. Now, in the case of the electric force, it's all very simple. It's a simple force law, inverse square, same as gravity in Newton's theory. And you can pull the electrons apart, the electron and the positron apart. So the force gets weaker and weaker as they get farther away. And if you look at the energy as a function of distance of these particles, it saturates, and that's called the ionization energy. If you kick an atom, out comes the electron, and then you can make it run in wires and work in motors and create the Industrial Revolution. But you can easily pull electrons out of atoms, which become ionized. Now, the claim, our understanding at this point now, is 100 years after Maxwell, is that the force between quarks is exactly the same in a sense. And the only difference being that there are 3 such charges, not just one electrical charge, and that the quarks don't live in the classical world that we're accustomed to, but rather in a quantum world. And in that quantum world, we have to revise, we had to learn what the structure of the medium in which these quarks live is. And by the medium, I mean what fills up the space. What is the vacuum, the empty place in which we put these quarks? Our usual picture of the vacuum is there's nothing there. Then you put matter into the vacuum, and there's some force acting on that matter. But in quantum mechanics, you can't really have an empty, nothing, inert vacuum. You can't even have an inert oscillator. Classically, an oscillator, like a pendulum, a simple system with 1 degree of freedom, can move back and forth. In fact, I thought I had it moving. There it is, moving. But in its lowest energy state, if you remove all the energy, cool the system down to 0 degrees Kelvin, the classical oscillator disappears. There it is, at rest. Now, in the real world is quantum mechanical. And Heisenberg taught us that this situation cannot be an accurate description of the quantum mechanical vacuum. Here's the quantum oscillator, and we following Heisenberg's way of thinking, we try to operationally determine that this oscillator is indeed at rest. So how do we determine that? We look at it. What does it mean to look at it? We shine light on it. Light comes in these quanta of light, always carrying some energy, and that changes the state of the quantum oscillator. We learn, one of the earliest results of quantum mechanics, that every such degree of freedom, every such dynamical object in a quantum system has some kind of zero-point motion, oscillation. It's fluctuating. Now, the strong force, as we learned, is mediated by a field that acts on a charge, a strong charge. There are actually 3 such charges. We've called them colors, in the lack of a better term, to distinguish 3 charges, 3 labels. We could have called them 1, 2, 3. Instead, we call them red, white, and blue. These are red quarks, which carry the red charge. This is a red antiquark, a red quark, opposite charges. They set up, if it was just classical physics, a field called the chromodynamic field because it acts on the color charge instead of the electric charge. And it gives rise to forces that fall off like inverse square law, just like E&M. By the way, if this was the case, you would have known about these quarks and this force, just like you know about electricity and magnetism, acts at large distances. You could shake these quarks and create waves, which would be colored versions of light, and quite complicated. But these quarks live in the quantum vacuum. And this is a picture using our theory of what the vacuum looks like at the scale of the proton. The proton's about this big in this picture. And this is a picture, sort of a picture derived from calculations, lattice gauge theory, computer calculations of the fields that arise when you have these quarks in the vacuum. And these fields are there because they're, in a sense, an oscillator at every point in space, which is fluctuating back and forth. And this is what it looks like. If you want to come away with understanding a very important feature that we've learned the last part of the 20th century was that this is what the vacuum looks like, much better than your picture of nothing, which is the usual picture of an inert, empty vacuum. And in this complicated medium, the force law between the quarks changes. The vacuum abhors having these flux lines penetrate through it, tries to squeeze them down, can't completely because there are these charges that create them, so it squeezes those lines of force, flux lines, down to a tube-like object. And it's fresh, high school mathematics to work out that if that's the case, the force law between the quarks does not diminish as you pull the quarks apart. Does not fall off like inverse square law, in fact, remains constant. At a more subtle level, you find what John referred to, asymptotic freedom. In fact, that's what led to this theory, because the force actually gets weaker when the quarks are closer together, explaining what hints at this kind of phenomena from experiment that motivated this discovery. And that produced this theory called QCD. And this is what it actually looks like when you pull quarks together in a computer lattice gauge theory calculation of the field lines that are produced. So it looks very much like, you see the field lines start out spherically symmetric when they're close together, and then they get confined to this tube. Looks like a fat string. In fact, this is how string theory began, in a sense, to explain those things. And now when you calculate the energy it costs to pull the quarks apart to a larger distance, it continues to increase. Farther and farther you pull them apart. And that's why you can't pull quarks out of nuclei or atoms, and you don't have quark currents and quark motors, and that's why all of the quarks are permanently confined inside neutral protons. And the reason you don't feel this strong force, which is much, much stronger than electricity and magnetism, is that all the objects that have this colored charge are actually neutral. They're all strongly bound inside nuclei, and no matter how much energy you kick them, they can't come out, because force law, the energy gets bigger and bigger the farther apart they are. So this is a very successful theory. It explains how nucleons are made out of quarks, which are, unless you do something dramatic like heat up the world or a system to millions of degrees Kelvin, you're not going to ever see a quark. Instead, you're going to see all these hadrons. But the theory essentially has almost no parameters and allows you to calculate precisely what the masses, the spectrum of those confined quarks is. Okay, that's a bit about the Standard Model and its power. And the amazing thing being that electricity and magnetism and the strong nuclear force are at the bottom theories we call local gauge theories, but they're theories which produce forces because of the conserved charges of the constituents in a way that is very similar were it not for these very interesting quantum effects. But what we're really interested in physics always are the unanswered questions, and there are many that the Standard Model, standard theory, does not answer. There are experimental hints that there has to be something else, particular dark matter, a new form of matter which is not explainable by quarks, leptons. Neutrinos have masses. We have a lot of matter and very little antimatter in the universe. We would like to be able to calculate that. And there's this weird fact that astronomers have discovered that the universe is expanding at an accelerated rate. There are theoretical issues that cry out for explanation. The most motivating for me, at least, has always been the hints at unification. All these forces are the same kind of force. It's natural to try to unify them. You have the issues within the Standard Model of hierarchy of scales, which seems a bit weird. You have all those quarks with masses and mixings that nobody can at all calculate, just has to measure. And then you have this vacuum energy, which presumably Einstein's cosmological constant, that is responsible for the accelerated expansion of the universe and whose origin we don't understand. Now, these issues, some of them have been around for a long time. Some of them are rather new. Some of them hint at new physics that is discoverable at the new accelerators like the LHC. In particular, these guys, which might suggest something about supersymmetry, which I'll come to. But let me say a word about unification. So physics, one of the achievements of physics over the centuries, starting with Newton, has been unification of different aspects of nature, of our description of physics. Newton, after all, said something that was too the few scientists of his generation rather surprising, namely that the motion, of pointers or apples is described by exactly the same laws, mathematical laws, as the motion of the moon. That's remarkable that the unification of those phenomena of nature, this has been a constant theme of fundamental physics. Electricity and magnetism, quite different, apparently, normal energies phenomena, were unified by Faraday and Maxwell with the invention of the electromagnetic field and the realization that they were really the same thing as viewed in different ways. Standard model has all these different components. It has two kinds of matter, quarks and leptons, electrons and neutrinos and quarks. And it has three forces that act within the nucleus, within the atom. Electromagnetism, a weak nuclear force, two charges, one charge, three charges. If you have one charge, two, maybe you put them together and you just need, with 5 or 10 or 5 charges, you could unify them. And indeed, as soon as the Standard Model was formulated, people thought of doing this, and remarkably, the different components of both force and matter fit together. So these are like pieces of a jigsaw puzzle. And you ask yourself, I have a few pieces. Can I put them together to make a coherent picture? Not necessarily. You might be missing a few. You might have to go and look around for some new pieces that are in the corner and it wasn't necessary. A very simple way is these 3 kinds of force and 2 kinds of matter fit together into a whole variety of bigger theories, if you want, that contain all the forces and all the forms of matter, and then are split apart by effects that we've learned to understand in many different branches of quantum physics. Some of the simplest kinds of generalizations of the Standard Model put, in fact, all of the observed particles, fundamental constituents, and all of the observed force to a very beautiful and symmetric generalization. Based on, if you want here, a theory with 5 charges or 10 charges, depending on how you look at it. Now, this might appear a bit bizarre. When you fit electricity and magnetism together, as Maxwell did, they really fit like this. There was no need to explain anything else, except to understand what essentially was Einstein's principle of relativity. So until Einstein, you might say that nobody really understood E and M. But in the case here, there are obvious problems because these forces look very different, and there are physical reasons for that. But how can they be both unified and different at the same time? And that I really don't have time to explain, but it's partly because the underlying principle in both classical electromagnetism and in the Standard Model is a local symmetry of nature. We've understood that although those symmetries might be symmetries of our description of nature, they might not be manifest in that vacuum. A lot of examples of this, for example, one right before us. You all know that the laws of physics are invariant under symmetric under rotations, right? When I publish a result, or my colleagues do an experiment, they don't have to put in the paper that their laboratory was facing north. Could have been facing south. It doesn't matter. They're going to get the same answer because the laws of physics don't depend on rotation. But this room is described by physics, and it is not rotationally invariant. Right now, I look this way and I can't see you. Look this way, I can't see you. So the room is not rotationally invariant. The laws of physics, however, are. So why isn't the room rotationally invariant? Well, you all know why the room isn't rotationally invariant, because you came in from there and you sat down here, and you're not there. But you would imagine that if I took everything out of the room, all the atoms, leaving nothing behind, in other words, I'd create a vacuum, that would be rotationally invariant, right? How else, what else could it be? And with the classical picture of the vacuum containing nothing, that's kind of obvious. But I showed you what the vacuum looks like. It's pretty complicated. And it is perfectly possible that certain symmetries of the laws of physics can be broken by such a complicated vacuum. And that can cause the differences of this unified force as looked at short distances, where you don't see the structure, compared to large distances. But if all the forces are unified, you'd think that there wouldn't be a strong force and a weak force. They'd all be the same strength. But that we learned with asymptotic freedom isn't the case. So soon after Standard Model was completed, people tried not just to unify the forces, but to see whether they became equal in strength when extrapolated to very high energies, or conversely very short distances. Now the nuclear force, as I explained, gets weaker and weaker when you bring the quarks closer and closer together. Electromagnetism does the opposite, gets stronger and stronger. It's an interesting fact about the quantum vacuum. So when you extrapolate to high energies, they do tend to come together. And this was quite amazing. In fact, it occurred at very, very high energies, or very short distances. Not that we measure here, but we extrapolate. As theorists, we can do that. Very close to the point where gravity becomes a strong force. Now, you all know that gravity is a very, very weak force. And some people find that hard to believe, because it's the only force they ever felt. Everyone feels it in the morning. Get up, you feel gravity. But the reason you feel gravity, even though it's by far the weakest of all forces in the macroscopic world, is that it's so weak and you can't screen it. So you don't feel electricity and magnetism unless you on a dry day, create a little static, then you can feel a jolt of electrical current. But normally atoms are neutral. You don't feel electrical forces, you just feel a remnant. You certainly don't feel the nuclear force, because the objects that carry the charge and feel the force attract each other so strongly that they're confined within these neutral nucleons. So you don't feel that force, except a very weak remnant of it, which, by the way, is strong enough to make nuclear weapons much more powerful than electrical chemical weapons. And in the case of the weak force, there's another reason, which I won't go into, why you don't feel that. But at this energy, they would all be equally strong. And gravity is really weak, but it acts coherently. There is no such thing as anti-gravity. Gravity is sourced by energy, by mass, right? Mass is the source of gravity. Mass is energy of an object at rest, according to Einstein. You feel gravity, pulls us down, because the whole Earth, which is like 10 to the 55 atoms, are all pulling on this pointer. Now, the fact that I can hold the pointer up with the whole Earth pulling on it, right, with a little bit of electrical chemical force, is just a demonstration that gravity is really, really weak. And unless you put a lot of particles together to form planets and suns, you're not going to feel it. It, in fact, is 40 orders of magnitude weaker than these other forces within the atom or within the nucleus. However, it's sourced by energy, by mass. So if particles have a lot of energy, they attract each other much more strongly, and at this very high energy, gravity becomes equally important. Well, this is a theoretical extrapolation of theory and our measurements of these forces at low energy. What does it tell us? Well, I regard it, and many of us, as a very important clue for the unification of all the forces of nature that we know of with gravity at this very high energy or very short distance. But it could be a coincidence. The great thing about physics is these are both possibilities. We don't know. This is could be regarded as a clue as to what it's really telling us, and a clue as to what you should work on, and many of us have for the last 40 years. Or it could be an accident. It doesn't particularly tell us anything about how the forces unify, this kind of picture, and it's very depressing. And this is one of the reasons why high energy physics, fundamental physics, is so difficult. It's not because of the nature of nature. The fact that it seems that the fundamental scale is really very far away from where we presently do observations. And this linear scale of distance and energy is not the right way to look at it. But that's the way we have to build machines to explore. We do, however, have some hints that there's new physics of a fascinating type around the corner. We've had those, again, based on various clues. But let me just say a word what this supersymmetry is. So as I said, our description and our understanding of the physical world has often developed by discovering new symmetries of nature. For example, that laws of physics don't change when you make rotations. So supersymmetry, roughly speaking, is the symmetry under rotations as well, but in a bigger space, which we call superspace. So roughly speaking, you just add the word super everywhere. So I tell you what superspace is. Well, superspace is a bigger space than space and time, which we call space-time, which is the arena in which, until recently, we've formulated our theories. We have space, particles live in points in space and move as time goes on in space-time. And our basic theories of physics are unchanged by various rotations in space-time. So I don't have to say where my laboratory is, because the laws of physics don't change as you translate in space. And I don't have to say what direction it's pointing, because the laws of physics are invariant under rotations. And by and large, I don't have to say which day of the week I did my experiment, because the laws of physics are invariant under time translations. So supersymmetry says there's a bigger space, and the laws of physics are invariant under rotations in this bigger space. But the really interesting thing about this bigger space is that the new dimensions, the new coordinate axes we had, are measured with anti-commuting numbers. And anti-commuting numbers are numbers whose multiplication depends on the order. Theta 1 times theta 2 is minus theta 2 times theta 1. Now it turns out that you can make sense of such numbers. Mathematicians invent all sorts of strange numbers, like square root of -1. These are not as strange as complex numbers, imaginary numbers. But you can also generalize all of the theories we know and love in physics to theories that live in superspace. You simply now call them supertheories. And they just have, if you want, particles at points in this larger space, or fields that permeate this larger superspace. And there's a generalization just about of all the theories we have in physics, which supersymmetrizes them, embeds them in this larger space, and then says the laws of physics are invariant in addition to ordinary translations, rotations, to translations, rotations in superspace. Now, this is mathematically very beautiful and elegant and very useful in mathematics as well as physics. But from a physics point of view, there are real clues from observation and from theoretical speculation that this generalization of our ordinary physical theories might be actually present in the real world. And the reasons have to do with, I want to explain this puzzle, but partly with making that unification of all the forces really tenable, and partly with the existence of this other form of matter I said a word about before, dark matter. So what about unification? Well, I said this is a picture in the standard theory model of the extrapolations of the forces of nature. This is actually on a logarithmic plot, straight lines. This is the 1 over the strength of the force. And in that way of picturing it, this is the strong force which is getting weaker. This is the electric force which is getting stronger. And these lines should meet at a point if this unification takes place. And nowadays we have much better extrapolation than we did in the beginning, and better measurements, and they don't meet. So that could be, well, forces aren't unified. Or we've left something out. And it turns out that if you just add supersymmetry, you do the minimal thing to embed the standard model in a superspace, now that supersymmetry has a scale of structure in the vacuum, and if you put that around a TV, then the forces do meet to 1% accuracy after extrapolating over 18 orders of magnitude. Quite remarkable. An important clue for both supersymmetry with the new structure of supersymmetry being visible at 1 trillion electron volts and unification, or a coincidence. And then there's dark matter. The astronomers looking at the motion of planets in other galaxies and our own, and in galaxies and clusters of galaxies, have deduced from the laws of gravity that the universe must be full of a form of matter that pulls another matter, bends light, but is not visible. It's dark. It's not the kind of matter we're made out of. We are not the stuff that galaxies are made of. They believe that the Milky Way doesn't look just like this, but is a clump of ordinary matter, nuclei and atoms, in a big halo of dark matter, which weighs 20 times more, has more mass than in all of the galaxy, the 10 billion stars that make up the galaxy. Indeed, they believe that 90% of the matter content of the universe is made of this dark matter. Dark means that it doesn't emit light, doesn't interact with electrons and quarks and shake them around and emit light. But if you assume that it's just some kind of heavy particle that is sort of like the particles we know about, but doesn't have all those charges that give rise to those forces, then you can explain the dynamical behavior of galaxies and clusters of galaxies. Indeed, you can give a concise history of the universe from the observed microwave background era till today. Quite a remarkable feat. But you need to assume that there is this dark matter, and it really has been measured, and in this indirect way. They call it WIMPs, weakly interacting massive particles. We've never seen them. And we don't know what they are. And we're looking for them. We're looking for them underground. So, if WIMPs exist, then roughly 500 of them are passing through each of you every second. And not causing cancer. So you might feel happy about that, and you should, but physicists feel kind of sad because we could detect these particles if they did something to you. But they rarely do. They just pass through you and the whole Earth without a collision. But if you wait long enough and you have a big enough detector and there's a lot of flux, eventually you'll see one of them hit an atom, cause it to jump off, and you will detect WIMPs. So people have been looking for that underground for years with more and more accuracy. People have been looking for them in the sky. These dark matter particles have antiparticles. They can annihilate, give rise to bursts of radiation. If they're out there, they should do that some of the time, perhaps. And so we've been looking for detection of dark matter in the galaxy. And we've been trying to produce dark matter. You can produce any form of matter because they're, according to the basic fundamental understanding we have, there's always antimatter as well, and you can produce dark matter and anti-dark matter if you have enough energy. But still, what are they? They don't fit in the standard model. There's something new. And one of the neat things about supersymmetry was that, although not invented for this purpose, again, it naturally predicts a candidate for dark matter, which is of the right type, so that if in fact some of the new particles that supersymmetry predicts will occur at around a TV, you could explain the dark matter content of the universe, starting with a hot Big Bang, which is how we think the universe evolved. So again, that's a very important clue for supersymmetry, and picks out again the range of energies of the LHC where we might see it, or a coincidence. This is life in fundamental physics, and people have to make bets on their life's work based on these clues, which might be coincidences. So this is what is being looked for at, say, this is a hypothetical discovery of supersymmetry at the LHC. What you see here is a collision, and then these detectors that observe two jets of particles, one going out here, one going out here. There are a few other particles, electrons, muons. But you just look at this and you see all this stuff going out this way, energy, momentum, those are conserved. There has to be something going this way, right? It's as if I'm just standing here and suddenly, boom, I go that way. What pushed me? It's got me asked to go the other. It's Newton's third law, right? So this could be interpreted, perhaps, it's called missing energy, missing momentum, and as a sign that some particle came out and wasn't detected, didn't interact, just like these dark matter particles. It could be a neutrino. Neutrinos behave like that as well. That's a background for this kind of detection. But this is what they're looking for to be a detection that you've created dark matter in the laboratory. Not yet, they haven't seen it. But I want to tell you when you someday open the paper, hopefully in the next year, and you read that scientists at CERN have discovered, or they claim, hints that might be supersymmetry, that what they're really discovering are quantum dimensions of space and time. Now, that symmetry isn't manifest because the vacuum's complicated. We know that. But it still, if correct, will be a property of our description of nature, which will lead us to the conclusion that although the vacuum is complicated, we live in a space-time with quantum dimensions. Quite a revolution in the way we think about space-time. But we haven't seen it yet. Might not be there. In fact, we don't know what will be discovered, if anything, at the LHC. So let me say a word about the future of particle physics, the fundamental physics. So I like to describe the situation now in terms of two extreme scenarios, that of the optimist, that of the pessimist. Because of the difficulty of looking for these fundamental laws, physicists often oscillate between the two. You have a new idea, speculation, theory, doesn't work, back and forth. Same with experiment. I'm an optimist. Optimists, most of my colleagues are optimists. Not all, but most. The pessimists tend to leave the field. You need to be optimistic to stay in this kind of game. The extreme pessimistic scenario is based on, well, for example, even the newly discovered features of the standard of high energy physics, like the Higgs, just fit the standard model. In this scenario, the Higgs particle and the things it interacts with are described perfectly by our existing theory. So we learned nothing particularly new from the discovery of the Higgs. There's no signal for supersymmetry or anything else at the LHC. Could be no detection of dark matter in the sky, underground, or at the LHC. And most importantly, no indication of where the next threshold is. So that's extreme pessimism. What to do? Who knows? In my opinion, if that is the case, then we must proceed and fully explore the somewhat larger range of energies, which takes us into the 10 to 100 TeV energy range. Now, the more likely scenario, in my opinion, is the extreme optimistic scenario. These new particles, the Higgs particles, show some deviation from the standard model, and they're a new kind of particle that has never been observed before. They have different kinds of couplings. They couple to everything. You might use them as ways of discovering new physics, and that will happen in the next few years. You will actually start producing these supersymmetric particles that we've been waiting for, and I can collect my bets. We will detect dark matter both in the sky and underground at the LHC. And we will have strong guidance for the next steps, in which case we should fully explore the new domain of fascinating physics that we uncovered. And there are, of course, plans to do that, which are well underway at a linear collider of electrons and positrons in Japan. There's a lot of talk at CERN about their ultimate future beyond the LHC with a 100 TeV collider under Lake Geneva in the Jura. Quite amazing project. Unfortunately, there's very little talk about this laboratory, which is located in the Midwest, called Fermilab. But there is talk about in China, which is very interested, perhaps, in constructing what I like to call the Great Collider. This would be 100 TeV, 10 times the energy of the LHC collider around here near Beijing. This is not an impossible dream. It's not particularly an expensive dream. In fact, we built this machine last century, and then Newt Gingrich and his friends came along and killed it. It was called the SSC. If we hadn't done that, we would be running now, probably upgrading that machine from 40 TeV, 3 times as powerful as the LHC, to 100 TeV at this very moment. And many of these questions would have already been answered. But, you know, we had to, I forget why they did it. Maybe somebody remembers. Space station. No, that was why the Clinton didn't support it at the end. But I have no understanding of the contract with America. Anyway, we don't do that kind of thing in this country anymore. But the Chinese intend to, perhaps. We'll see. So we're still pursuing this goal, how the forces unify. I'm running out of time, so I'm going to go rather rapidly. We've been led to string theory years and years ago. String theory is one of the most oldest speculations we have. But it has the ability to truly unify these forces with gravity. And as far as quantum gravity goes, is the only game in town. So a word about string theory. It came out of QCD, or it came out of hadronic physics. It arose because one was trying to explain these flux tubes, which describe originally quark-antiquark pairs, and were the origin of a phenomenological approach that remarkably led to a totally new kind of theory of matter in which the objects, the elementary objects, were extended, string-like, open strings. Now, one of the most remarkable understanding that emerged finally was that these string theories that sort of we were led to by trying to understand the nuclear force are really indeed the same as gauge theories in a fundamental way. But originally they seemed very different. And even more so when one realized that open strings could close, and those oscillating objects didn't describe anything that looked like quark-antiquark pairs, but rather gravity, gravitons, the quanta of Einstein's theory of gravity. That was the origin of string theory, and it had the potential for describing all those different particles in a unified fashion by making them different vibrations of one underlying, more complicated object, namely a string, which can have an infinite number of shapes or harmonics. That goal, which motivated many of us 30 years ago, enormously exciting, has turned out to be more difficult, but it led to incredible insights into the possibilities that lie beyond our current understanding. For example, the potential existence of more than 3 dimensions. Since the simplest versions of string theory quantum states required that those strings were oscillating in 10 dimensions of space-time. So some of the dimensions, well, to have even a crude description of the world we see around us, the other extra 6 dimensions would have to be curled up, and indeed there were solutions, consistent so-called compactifications of string theory in which 6 of the dimensions were curled up in an absolutely beautiful way. And this is a kind of illustration of a 6-dimensional Calabi-Yau manifold, a very special, beautiful geometry of 6 dimensions are curled up like you curl up 1 dimension to form a circle. And the idea is that at every point in space, like this point, it actually isn't a point, but a little 6-dimensional manifold like this. And when you tried to work out these strings, such a manifold, you discovered that they gave rise to very special kind of forces, exactly the ones we see in nature, those kinds of electricity, weak, strong nuclear forces. Oops. They produce exactly the kind of form of matter and exactly the mass. Well, they produce massive chiral, they're just what we need for the Standard Model. And all of those specific forces, matter, values of their masses were dictated by the internal geometry. This was enormously exciting because it gave a unification and a geometrical explanation of all of these things that the Standard Model must take as input. Unfortunately, it turned out that there wasn't just one such quantum state you can construct, but zillions, and no principle to choose among them. And so string theory turned out to be, in a sense, not really a theory. So let me give you my feeling as to what the framework of physics, theoretical physics, is at the current time. The Standard Model is formulated in terms of field theory, like electricity and magnetism, except it's quantum field theory, which makes it more interesting. But quantum field theory isn't a theory, it's a framework in which we fit and construct specific theories like the Standard Model. Then we have string theory, which isn't a theory either. In fact, it's even worse. Nobody can write down the principle on a t-shirt. So it's not a theory. We don't have equations or a principle. We have our ad hoc rules for constructing consistent quantum states, if you want. What we've learned recently is, first of all, these two different theories, neither of which is a theory, are really the same thing. In many situations, we can use either specific quantum field theories or specific string theories to describe exactly the same phenomena. They're dual descriptions of the same thing. So most likely, these two frameworks are really the same and part of something bigger which we're exploring. And this isn't a theory, but a framework within which we embed the Standard Model, which is really the standard theory. That's a theory. It leads to specific equations and hard predictions. These are frameworks. And in turning this incredible framework that includes fields and strings and higher dimensional objects, quantum gravity, and the forces of the Standard Model are all specific parts of this framework. What is the total framework, even? We have no idea. Still exploring its structure. And what is the specific theory within this framework that would allow us to make predictions and calculations? We don't know either. But the understanding that you can describe the same physics by field theory, quantum field theory, which is the basis of Standard Model of particle physics, as well as condensed matter physics, many-body theory, and equally well often by the behavior of strings or brains, has given us incredible new insight into the gauge theories that underlie quantum chromodynamics. And, for example, the qualitative and even semi-quantitative understanding of the quark-gluon fluid that is observed at RIC at very high energies, as well as the behavior of strongly correlated electron systems and the critical points that condensed matter physicists are interested in. It has given us new ways of trying to resolve some of the deep conceptual problems and puzzles of quantum gravity, like the behavior of black holes, and most importantly, my point of view, it's given us even new handles on what space-time is. Since from the beginning of string theory, from early on, we had many indications that the way of thinking about space-time as the fundamental arena where physics operates is wrong. Many of the properties of space, time, disappear in string theory. Smooth manifolds, fixed topology, even the fixed number of dimensions, no longer meaningful. In fact, long suspected that space-time is probably eventually going to be understood as an emergent concept, proximate. After all, why should it be? We've learned that it's not a rigid, given Newtonian-like structure. It's dynamical. It oscillates wildly, especially at short distances, because of quantum mechanics. It and its dynamics, which is gravity, are most likely best viewed as emergent. But emergent from what? And how do you start with something and without space-time and even do physics, especially without time? So that's one issue that we face, and we've learned a lot about how that might be resolved, but we're far from understanding this in detail, especially time. But then there's another issue that physics that we have to encounter and deal with now in high-energy physics. And that is, what fixes the dynamics? We have this framework, but a theory is a particular example that fits in this framework. You can describe the framework of all theories, but that doesn't allow you to make predictions. We have one world, we think, I think. We have to make predictions, so we have to know what principle fixes the dynamics. And for the first time, we have to know what fixes the initial state. We know a lot about the initial state. In fact, the whole history of the universe, again, all within the last century, from the beginning, or close to the beginning, till today. Incredible story, which works in standard model or theory of cosmology. But there's always a beginning, the Big Bang, which means where all of our understanding breaks down. And in a sense, to be intellectually honest, and maybe even to be predictive, we can't avoid this issue anymore. We have to ask how the universe began and what the initial conditions were. Now, before we got to this level of understanding, we could avoid that question. Who cares how it began? Because we're just describing what goes on in this room at this time. But once we're doing quantum gravity, trying to find the theory, we're actually trying to find the theory of the universe. The answer is the whole universe, the space-time history. Now, maybe we can approximate that without worrying about the initial condition, the beginning, but there's only one universe, observable universe. We need perhaps to know that. That's close to this same scale of energies and distances where the unification takes place. We perhaps need to know what happens at a boundary, if there is a boundary, and at the end of. We don't know what the rules for answering such a question are. We don't even know whether that's an appropriate question for physics to answer, because we've never had to do it before. So this is one of the big, I believe, stumbling blocks in our attempt to construct a specific predictive theory, because with our current understanding, it would have to be a theory of space-time. And as Einstein told us, that's the history of this manifold, the beginning to the end of space-time. So, we have a wonderful theory of elementary particles, but most of the most exciting questions remain to be answered. We have fantastic instruments and experiments, which in my opinion have a long history to go. Fantastic speculations, and as always, the best is yet to come. Now, I have another 5 minutes if you give me time, but I have overspoken, so maybe I'll stop here.
few questions.
What's the next 5 minutes?
Well, the next 5 minutes, I always find that people enjoy, because I ask the question, well, I guess I ask the question, you know, I got pretty ambitious at the end of this talk, right? And theoretical physics is getting pretty ambitious. Can we go on forever? And there are 3 issues here that I'll just say a few words about. You know, the questions I was raising are kind of fundamental. It's hard to think of questions. If we were to answer those questions, would there be other questions? Can we construct a final theory? Can we unify all the interactions and describe the initial state of the universe at its end state? And, you know, what else is there to do? Is that possible? Well, we might not be able to go on forever because we might simply be just too dumb. I mean, these are tough questions. How did the universe begin, right? And what is space-time? And finally, we might not be able to go on forever because we might lose the will to proceed one way or the other. So I want to say a few words about these issues. Is there a final theory? The theory of everything, sometimes it's called string theory, sometimes was blamed for being a theory of everything, or held out to be a potential unified theory of all the forces. So in my opinion, this is a geometrical issue. This has to do with the geometry of knowledge. So there is a well-known model of knowledge called the onion model, which I don't like. So in this model of knowledge, you know, our understanding of reality is an onion, and you peel away the layers, and you get to the core, and there clearly is a final theory. In the case of the onion, you might cry a lot, but you'll get to the bottom of it. Anyway, I don't think that's a very good description of knowledge. I like sort of the opposite. We live in a sea of ignorance, and we're pushing outwards. And so knowledge is this region. Might be separate islands, but they usually tend to merge. And we're aware of the boundaries, you know, where we don't know what's going on just beyond our current knowledge. And so this model of knowledge is, like every good theory model, should explain something. And it does explain one fact about knowledge that we all become aware of early in our life, namely that although knowledge increases as this bubble expands, so does ignorance. Ignorance is really confined to the surface of the sphere of knowledge, because you can't be ignorant of something that's really far away. You don't even know how to formulate the questions. So this explains both that something we all know. The more we know, the more we're ignorant of. Our ignorance increases. And also explains why we get wiser, because, you know, knowledge increases like the volume, whereas ignorance like the surface. So good. This is a model that explains something we all encounter, and, you know, the more we know, the more we don't know, but we get wiser. So now we can ask the question of, can we construct a final theory? And that should be reformulated geometrically as, is there a finite amount of ignorance? And we've run into this situation before in the exploration of the Earth. So this is a map of the Middle Ages, a European view of our knowledge of geography, and explorers were exploring the boundaries where they were aware that they didn't know what was there, the ignorance. And they could have gone on exploring forever, except that the Earth is round, as you know, and they learned. And so they ran out of ignorance, unexplored territory, explorer societies shut down. You know, there was a final map, or a pretty good map, of the Earth. So the question is the sea of ignorance that I described before compact? So two possibilities. One is that it's unbounded and infinite like the flat Earth, in which case you can go on forever. There's always more ignorance. You never run out of ignorance and never have a final theory. But it could be compact and finite, and the story could come to an end. You'd know this when the ignorance started decreasing. Eventually you'd run out of ignorance and you'd cover the whole sphere of knowledge, and that would be a final theory. Well, at the moment we only have local knowledge. We don't really good enough measurements of the domain of knowledge, and historical experience has been that whenever we explore some new territory, we only discover that ignorance gets bigger. And there's no sign of curvature, either positive or negative, so I'm agnostic. Could be compact, finite, or non-compact and infinite. But even if we, by the way, of course, had such a final reductionist theory, it wouldn't be the end of physics or science, because most of the new stuff we discover and the most fascinating aspects are not by going up the reductionist limit to the theory of everything, the reductionist theory, but the seemingly infinite ways in which you can put together the microscopic structures to form complex, interesting structures. But there's another reason we might not be able to go on forever, answer some of those questions, even if the universe is compact. If ignorance is compact, because we might be too dumb to proceed. Why should we be arrogantly believe that this stage in evolution, we, the king of the world, are smart enough to understand the origin of space-time or the initial state of the universe? After all, we're very well aware that our neighboring species are clearly limited. You cannot explain to my dog the Schrödinger equation, and I know that there's no way he'll ever be able to understand the Schrödinger equation. So why should we imagine that we're not the same? It's pretty arrogant. But I think there's some reasons why we might avoid this problem. One is that we have a kind of infinite capability, and that's language, whose highest form is mathematics, and it clearly has an infinite capacity. As Chomsky explained about ordinary language, a baby that has the inherent ability to learn language rapidly as an infant can utter sentences that no one has ever uttered before. That's an infinite capacity of language, and mathematics surely has that as well. Now, there are many kinds of infinity, and the infinite capacity we have might not be infinite enough. But I think we would begin to notice that if we were getting close to that cliff, the dog cliff, right? We would begin, for example, graduate students entering mathematics or physics would take longer and longer to get to the frontiers, and they don't. Still, the most brilliant young scientists or mathematicians, same early age, can rapidly advance to the frontiers and make significant contributions. There's no sign that we are being, so far, faced with questions that we are unable to answer. And even if we were, then we would start changing ourselves, modifying our genes. Might do that anyway, probably will, but we could find other strategies to answer these tough questions. I think the biggest challenge going on forever, answering these seemingly fundamental questions, is just losing the will and means of both us and society to undertake these incredibly expensive and difficult, especially experiments, that we now face. And here, I just hope not, and end this added section with Hilbert's famous cry, "We must know, we will know." Thank you.
With that, we will